Hello everyone, I am Prathami and I welcome you to the 24th universe. In this video, we will be exploring the fascinating history of binary codes and how it got incorporated into computer systems. Also, we will look at the brilliant mind behind this revolutionary invention. I believe that understanding the basics of computer programming is essential in today's world, and I am committed to providing you with the best possible learning experience. To start off, let's rewind back to the ancient times. The systems related to binary numbers have appeared earlier in multiple cultures, including ancient Egypt, China, and India. Let us go to Egypt first. The Egyptians are known for their fractions and Egyptian multiplication, which is closely related to the binary system. In the 12th century BCE, the Egyptians used Horus-I fractions. Horus-I fractions were binary numbering system for fractional quantities of grain, liquids or other measures, in which a fraction of an Egyptian unit is expressed as a sum of the binary fractions 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32 and 1 by 64. The method used for ancient Egyptian multiplication is also closely related to binary numbers. Let us see that with an example. 24 multiplied by 35. The first thing that you have to do is write your problem out horizontally. The first number is our first column and second number is our second column. Underneath the first column, you always write the number 1 regardless of the number that is at the top of the column. You always double it, that is 2, 2 doubled is 4 and so on. You must stop doubling when you know that the next number would exceed the value at the top of your column, which is 24 here. At the top of our second column, we have the number 35. Whatever number you have at the top of your second column, you must rewrite that number and start doubling that number. Because we doubled 5 numbers in our first column, you may only double 5 numbers in the second column. So, we rewrite 35 and double it, that is 70, 70 doubled is 140 and so on. The next step is we must go back to our first column and locate the numbers that would have a sum of the first column, that is 24. The numbers that add up to 24 are 16 and 8, so circle those numbers. Now look at the adjacent column of the number that you circled it. It is those numbers that when added will give you the answer of your problem. Adding 280 and 560 will give you 840. The same idea is implemented by binary multiply circuits in modern computers. Now let's go to China. The I Ching or Book of Changes, as it's known in English, is believed to have been written by Fu Xi around 10th century BCE. The book contains 64 hexagrams and is used for guidance and decision making. It is based on Taoistic duality of yin and yang. Yin-yang originated in Chinese philosophy, describing an opposite but interconnected self-perpetuating cycle. Yin and yang are represented by broken and solid lines. Different construction of the three yin and yang lines leads to 8 trigrams. The different combinations of the two trigrams lead to 64 hexagrams. Gottfried Leibniz was perhaps the first major European intellectual to take a close interest in Chinese civilization. According to Leibniz, Chinese philosophy was similar to his own philosophy. He noted how the I Ching diagrams correspond to the binary numbers from 000, 000 to 111, 111. Now, let's move to India. The ancient Indian prosodist and a mathematician, Pingala, was the first to develop and use the binary number system while studying and analyzing Sanskrit poetic meters in his work Chanda Shastra, also known as Pingala Sutras, composed around 3rd century BCE. A prosodist is a person who studies chanda. A chanda means poetic meters. So, a prosodist is a person who studies poetic meters. A chanda shastra is a science of poetic meters. The Chanda Shastra presents a formula to generate systematic enumeration of meters of all possible combinations of Laghu, that is light, and Guru, that is heavy syllables, for a word of n syllables using a recursive formula that results in a partially ordered binary representation. That is, if we replace the values as g equal to 0 and l equal to 1 in the left side table, we would have this table on the right. Now, if we compare numbers with the Pingala's binary system and modern binary system, we observe that the Pingala's binary system is a mirror image of the modern binary system. Now, fast forward a little. In 17th century, a German polymath named Gottfried Wilhelm Leibniz wrote in his article Explanation of the Binary Arithmetic, which uses only the characters 1 and 0 with some remarks on its usefulness. Leibniz is also known for developing the modern binary number system, which is fundamental to the operation of modern computers, considered as such by most mathematicians. And even if you Google it, you will find the same answer. Leibniz had similarities with von Karamuel-Lowkowitz and Thomas Harriot, who independently developed the binary system. Von Karamuel-Lowkowitz worked extensively on logarithms, including logarithms with base 2. He was a Spanish philosopher, mathematician, and writer. Thomas Harriot was an English mathematician, astronomer, and alchemist. His manuscripts contained a table of binary numbers and their notations, which demonstrated that any number could be written on a base 2 system. Regardless, Leibniz simplified the binary system and articulated logical properties such as conjunction, disjunction, negation, identity, inclusion, and the empty set. In 1605, Francis Bacon, an English philosopher and scientist, discussed a system whereby letters of the alphabet could be reduced to sequences of binary digits, which could then be encoded as scarcely visible variations in the font in any random text. They are now called Bacon's cipher. This cipher uses 5-character sequences of 2 letters A and B to encode all the letters of the alphabet. A is encoded as AAAAA, B is encoded as AAAAB, and so on. Hello World would be represented in Bacon's cipher as the following. This is called a binary encoding. Bacon's cipher uses A and B, while computers now use 0 and 1. Bacon's cipher is the first time binary was used to encode letters. You might have already spotted a problem with Bacon's cipher. There are only 24 different combinations of a 5-character binary sequence, but there are 26 letters in the alphabet. In Elizabethan times, when Francis Bacon invented the code, the letters I and J were the same letter as were U and V. Now moving on to the year 1847. George Boole published a paper called The Mathematical Analysis of Logic that describes an algebraic system of logic, now known as Boolean algebra. Boole was a largely self-taught English mathematician, philosopher, and logician, most of whose short career was spent as the first professor of mathematics at Queen's College in Ireland. He worked in the fields of differential equations and algebraic logic and is best known as the author of The Laws of Thought, which contains Boolean algebra. Boole's system was based on a binary, a yes no, on off approach that consisted of the three most basic operations and, or, and not. This system was not put into use until a graduate student from Massachusetts Institute of Technology, Claude Shannon, noticed that the Boolean algebra he learned was similar to an electric circuit. Claude Shannon was an American mathematician, electrical engineer, computer scientist, and cryptographer, also known as the father of information theory. He was the first to describe the Boolean gates in electronic circuits that are essential to all digital electronic circuits, and he built the first machine learning device. In 1937, Shannon wrote his master's thesis, a symbolic analysis of relay and switching circuits, which implemented his findings. Shannon's thesis became a starting point for the use of the binary code in practical applications such as computers, electric circuits, and more. Then, there were few computers which tried to implement this binary arithmetic and Boolean algebra before we got introduced to ENIAC, but they were not that successful. George Stibitz was an American researcher at Bell Labs who is internationally recognized as one of the fathers of modern digital computer. He was also known for his work in the 1930s and 1940s on the realization of Boolean logic in digital circuits using electromechanical relays as the switching element. After his doctorate, Stibitz began working at Bell Labs. In November 1937, he built as a proof of concept the Model K, which was an early 2-bit binary adder. It used scrap relays and metal strips from a tin can. The K in the Model K came from a kitchen table upon which he assembled it. Konrad Zuse was a German civil engineer, pioneering computer scientist, inventor, and businessman. His greatest achievement was the Z3, the first fully operational electromechanical computer. Z3 was built in his workshop and was presented to the public on 12 May 1941. The Z3 was a binary 22-bit floating point calculator featuring programmability with loops but without conditional jumps, with memory and a calculation unit based on telephone relays. Despite the absence of conditional jumps, the Z3 was a Turing complete computer. However, Turing completeness was never considered by Sousa, who was unaware of the Turing's work and had practical applications in mind. This computer was destroyed in the bombardment of Berlin in December 1943 during World War II, together with all construction plans. Colossus was a set of computers developed by British codebreakers in the year 1943-45 to help in the cryptanalysis of the Lorentz cipher. Colossus is thus regarded as the world's first programmable electronic digital computer, although it was programmed by switches and plugs and not by a stored program. Colossus was designed by GPU research telephone engineer Tommy Flowers based on the plans developed by mathematician Max Newman at the Bletchley Park. The existence of the Colossus machines was kept secret until the mid 1970s. After the war, 8 out of 10 Colossus machines, which had been used to encrypt messages between Hitler and his generals, were dismantled to avoid their secrets falling into the wrong hands. The remaining two computers still found in the museum in Government Communications Headquarters, that is GCHQ, in United Kingdom. In 1945, we got our first computer, electronic numerical integrator and computer. It was designed by John Moseley and J. Presper Eckert. ENIAC was the first programmable electronic general-purpose digital computer. Other computers had some of these features, but ENIAC was the first to have them all. It was Turing complete machine and was able to solve a large class of numerical problems through reprogramming. And in this way, the binary code got incorporated into computers that made our life much easier. Just one thing to ponder over. Indian mathematicians have made significant contributions to the field of mathematics, but they are not widely known. Maybe because many of the foundational works by Indian mathematicians were developed centuries ago when communication and dissemination of knowledge were limited compared to the present day. Or maybe because the keywords and the text in Indian mathematics are written in ancient languages such as Sanskrit, Tamil, or Arabic, which may not be easily accessible or understood by a wider global audience. Maybe same is the case with other non-Western scholars. But thankfully, now the things are different. We can highlight and promote such contributions in the global mathematical community through conference, publications, and collaborations, and help to increase awareness about the contributions made by the ancient Indian mathematicians and other non Western scholars. I hope you learned something over here and found it informative. If you have any feedback or comment, please feel free to share them in the comment section below. If you enjoyed the video, please give it a thumbs up and subscribe to my channel for more educational content. Also, don't forget to share this video with your friends and family who might need this. Thanks for watching and I look forward to seeing you in my next video.